This is SpaceTime Series 29, Episode 64, for broadcast on the 29th of May 2026. Coming up on SpaceTime, a new explanation for how stars explode, Neptune's mysterious moon Nereid, and a safe return to Earth in outback South Australia for a hypersonic test vehicle. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study suggests that the neutrino, which are some of the least massive objects in the universe, may trigger some of the biggest explosions in the universe. Supernovae, the explosive death of massive stars, which is so bright it can outshine an entire galaxy. Neutrinos are the most common form of matter in the universe, but they're so small there are literally billions of them passing through you right now without you even noticing it. They're produced by some of the most extreme events in the universe, including the cores of stars, supernova explosions, and nuclear reactors. Neutrinos come in three types known as flavors: electron, muon, and tau. And what makes them really weird is that they oscillate between these flavors as they move through space. So, an electron neutrino produced in, say, a beta decay reaction may interact in a distant detector as a muon or tau neutrino. The cause of this oscillation between flavors remains poorly understood. Now, a report in the journal Physical Review Letters has found evidence that a particular rapid form of this oscillation, known as fast flavor conversion, may play a key role in whether or not a collapsing star explodes as a supernova. Stars shine by fusing hydrogen into helium in their cores. When the hydrogen runs out and it's all converted into helium, the star will then start to fuse helium into heavier elements, starting with carbon and oxygen. Now, for most stars like our Sun, that's where the process will end. The star will die and become a white dwarf. But for stars at least 8 times more massive than our Sun, they're big enough to continue this process, producing ever heavier and heavier elements until they eventually produce iron in their core. But no matter how massive a star is, it can't fuse iron into anything heavier. And so, the hydrostatic equilibrium balancing act between gravity crushing a star downwards towards its centre and nuclear energy pushing outwards ends, and gravity wins, causing the star to collapse under its own mass, triggering a shock wave which then blows the star apart in a core collapse supernova. While the neutrinos produced during this collapsing core are the main drivers of this blast, only certain flavours will interact strongly enough with surrounding matter to heat it up. And as a result, neutrino oscillation plays a key role. If neutrinos switch flavors at the wrong time, the explosion will fail. So to work out exactly what's happening, the authors developed new computer models of collapsing stars across a range of masses and incorporated fast flavor conversions in order to simulate how neutrinos interact during these events. They discovered that the outcome was closely tied to how quickly collapsing material was falling inwards onto the core, a quantity called the mass accretion rate. When the acceleration rate's low, fast flavor conversion boosts the energy deposited by the neutrinos and helps drive the explosion. Now, in contrast, when it's high, the conversion reduces the overall neutrino output enough to suppress the supernova blast. But the importance of the neutrinos doesn't end there. Pound for pound, out of all the particles with mass, neutrinos are the fastest. In fact, at one point, they were thought to be travelling at the speed of light. But because they do have mass, we know that's not possible, and that's now been confirmed. But exactly how fast are they? Neutrino physicist Kirsty Duffy and Durham University neutrino theorist Jessica Turner discussed exactly how fast neutrinos can travel in this report from Fermilab.
Neutrinos are really speedy. These little particles can travel straight through the entire Earth in a fraction of the time it takes you to blink. Pound for pound of all the particles with mass, they are the fastest, almost travelling at the fastest possible speed in the universe, the speed of light. But not quite. So exactly how fast are they? That's tougher to say. You may have heard that light from the sun takes 8 minutes to reach Earth. When you look up at the sun, you're actually seeing it as it was 8 minutes ago, before all those photons travelled 149.6 billion metres to reach the Earth. But some weird things happen when you travel at the speed of light, and if you're a photon, it seems like the journey takes no time at all. I've invited Jessica Turner to help explain it. Jessica is a neutrino theorist at Durham University. Hi, Jessica.
Hi, Kirsty. You're correct. To a photon travelling at the speed of light, the journey happens instantaneously. We move really slowly compared to photons, so our experience of time is immensely different. From Einstein's theory of special relativity, we know that the faster something travels, the more time slows down, to the point that for a photon travelling at the speed of light, time stops. So a photon experiences the entire universe's timeline all at once.
I mean, what? Think about that for a second. But why are we talking about photons when we're supposed to be discussing the speed of neutrinos?
The short answer is, on a practical level, neutrinos travel so close to the speed of light, you can basically just round up.
That's right. We've tried to measure the speed neutrinos travel by measuring how long it takes for them to travel long distances. For example, the Minos experiment timed how long it took neutrinos to travel 735 kilometers from Fermilab to northern Minnesota. But we don't have the resolution, even in our most precise experiments, to measure the speed of neutrinos being noticeably different from the speed of light. I mean, to the extent that we measure neutrinos at all. Now let's get a bit more specific. We can calculate the speed of a neutrino from its energy using Einstein's special relativity equations if we know its mass. Let's run the numbers for a neutrino we'd make at Fermilab's particle accelerators and give it an energy of 1 GeV. The other part of the equation is harder because we don't actually know the mass of the neutrino. We've never been able to measure it. There are some experiments that have helped narrow it down, including Katrin. Katrin recently showed that the mass of the neutrino has to be less than 0.8 eV over c squared. So let's say Katrin is just shy of finding the neutrino mass. We'll plug in 0.7 eV over c squared into our equation. That tells us that our neutrinos would travel at 0.99999999999999995 times the speed of light. To put that in context, the Andromeda galaxy is 2.5 million light years away, meaning it takes a photon 2.5 million years to travel here, at least according to us. If a photon and a 1 GeV neutrino set off at the same time from the Andromeda galaxy, the neutrino would arrive just 0.00004 seconds after the photon. That is how close to the speed of light they travel. So you can see why we have trouble measuring the difference. But then why are we so certain that neutrinos are traveling slower? One of the special things we know about neutrinos is that they change flavour as they travel. The fact that they can change tells us that, unlike photons, neutrinos experience time. And that tells us that they aren't quite travelling at the speed of light. But if you thought it was that easy to calculate the speed of neutrinos, just wait, there's more. Let's get into some of the weirdness of quantum mechanics. Neutrinos aren't separate. They actually travel as a mix of 3 different mass states: mass 1, mass 2, and mass 3. And each one has a probability of interacting as a different flavour of neutrino: electron, muon, or tau. This is an example of quantum superposition, and it is pretty wild stuff. Here's Jessica to explain it.
So an important thing to remember in this discussion is that particles are also waves, and the length of the wave is not infinite. So you can think of particles as little sections of waves or as a wave packet. When a neutrino is born at an accelerator, it starts out as a superposition of all 3 mass states. This means that the wave packets for all 3 mass states are overlapping. And as long as the wave packets are overlapping, you have a coherent neutrino. Any one of these mass states could be the one to interact in your detector, and you wouldn't be able to tell the difference. This leads to the phenomenon of neutrino oscillation.
But things with different masses should travel at different speeds. So what does that mean for the neutrino?
We do think that the different mass states of a neutrino should travel at different speeds. If the neutrino travelled for long enough, the 3 wave packets for the 3 different mass states would slowly spread out over time until they no longer overlap. This would cause what we call decoherence, and in that case we wouldn't see neutrino oscillation. we'd always have the same proportion of electron, muon, and tau neutrinos showing up each time. But to get these decoherent neutrinos, they'd have to have travelled an incredible distance, way further than any experiment we could ever build on Earth. The only neutrinos we know of that might experience this phenomenon are the ones that have been travelling since the Big Bang. Unfortunately, they're so low energy at this point that we don't have detectors sensitive enough to see them.
As you can see, examining the speed of neutrinos is anything but simple, and there's still more to uncover. Big Bang neutrinos, also known as relic neutrinos or the cosmic neutrino background, are one of my favourite neutrino physics topics.
Fun fact, when a neutrino is created, it's immediately going full speed. There's no acceleration period like your car. And while light can slow down while travelling through material, like water or air, neutrinos are basically always travelling at the same speed. This is because they aren't interacting with anything the way that light does through electromagnetism. So it takes the very expansion of space-time itself to stretch their wavelengths and slow them down.
Bonus fun fact. In 2011, neutrinos made headlines when the OPERA experiment reported a measurement that seemed to show neutrinos moving faster than the speed of light. Investigations showed that it was actually an equipment error in the experiment, and neutrinos do obey special relativity after all. Interestingly, one of the experiments that cross-checked the OPERA result was Icarus, which measured the same neutrinos as OPERA with a different timing system. Everything's coming full circle because Icarus was moved to Fermilab in 2017 and is now taking data in Fermilab's booster neutrino beam.
That's neutrino physicist Dr. Kirsty Duffy and Durham University neutrino theorist Dr. Jessica Turner in that special report from Fermilab. And this is Space Time. Still to come, Neptune's mysterious moon Nereid, and a safe return to Earth in the South Australian outback for a hypersonic test vehicle. All that and more still to come on Space Time. A new study suggests that planet Neptune's distant moon Nereid may be the last of the ice giant's original satellites, which somehow managed to survive a cosmic billiard game. Neptune is the 8th most distant known planet from the Sun, and it has 16 known moons, the largest of which is Triton, the only Neptunian moon large enough to have become rounded under its own gravity. Triton is a frozen world with a thin, hazy atmosphere, and it's peppered with cryovolcanoes erupting dark ice high into the sky. This ejecta is then blown across the moon's frozen nitrogen-covered surface by strong winds, leaving dark streaks across the ground as the material falls back to the icy surface. Triton orbits Neptune in retrograde, that is, in the opposite direction of its host planet's rotation, and it's the only large moon in the solar system to do so. And that's because Triton is thought to be a captured Kuiper Belt object from the frigid outskirts of the solar system that was caught up in Neptune's gravitational field billions of years ago. During that encounter, Triton must have scattered Neptune's original moons, putting them on destructive collision courses. One of the few exceptions to this fate looks like it could be the tiny moon Nereid, Neptune's third largest. New observations suggest that this 357-kilometre wide world was instead flung into an extreme elliptical orbit around Neptune. The study's lead author, Matthew Blakob from Caltech, says what scientists know about Nereid is very limited. For its size, Nereid is extremely understudied. It was discovered by Dutch astronomer Gerhard Kuiper 40 years ago. He named the moon after the sea nymphs in Greek mythology. Nereid's extremely eccentric orbit around Neptune takes a full Earth year to complete, ranging from 1.4 to 9.6 million kilometres. Like Triton, Nereid was originally thought to be a captured Kuiper Belt object. However, new observations by the Webb Space Telescope suggest that Nereid's composition is inconsistent with a Kuiper Belt origin. The new findings, reported in the journal Science Advances, claims that Nereid simply has too much ice, and that suggests that it could be part of Neptune's original satellite system. The observations show its elongated orbit matches what one would expect from a moon that was originally formed close to Neptune and was later pushed outwards by the capture of Triton. Balyakov says Neptune's innermost moons are likely to have been all formed from the shattered remains of the planet's original moons. In other words, they're Triton's casualties. This is Space Time. Still to come, a safe return to Earth for a hypersonic test vehicle, and later in the science report, a new study claims your eyes could indicate how strong your bones are. All that and more still to come on SpaceTime. Varda Space Industries' W6 capsule has returned safely to Earth, parachuting down into the South Australian outback. W6 was a demonstrator vehicle focusing on autonomous hypersonic flight and next-generation thermal protection systems. The capsule landed on Southern Launch's Coonabar Test Range in western South Australia, completing a journey that began with a ride into orbit on a SpaceX Falcon 9 transporter mission back in March. The W6 mission was funded through a partnership between the United States Air Force Research Laboratory and commercial space companies. The vehicle carried a payload from RIA space activity to further test the AutoNav autonomous navigation system. AutoNav traces its heritage to the software originally developed for NASA's Deep Impact program, where it autonomously guided a projectile into a comet at 36,000 kilometers per hour, generating an explosion equivalent to 4.8 tons of TNT. On W6, the algorithm operated aboard Varda's hypersonic re-entry capsule used onboard imagery to identify resident space objects, including stars and low Earth orbit satellites, in order to determine its precise position. The mission represents a crucial step towards fully autonomous celestial navigation for hypersonic and re-entry vehicles operating in dynamic environments. W6 also carried a nose tile developed by Sandia National Laboratory embedded with small samples of advanced thermal protection materials. The mission enabled researchers to evaluate material performance under real-life hypersonic heating conditions. As well as that, there were 2 instrumented shoulder tiles on the heat shield collecting in-flight thermal and performance data for NASA. These tiles were made at NASA's Ames Research Center in California's Silicon Valley using an alternative production technique called ECHAR. Together, these 3 payloads have generated valuable data supporting continued innovation in thermal protection systems for reusable re-entry vehicles and hypersonic platforms. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with a science report. A new study claims your eyes could indicate how strong your bones are and if you're developing osteoporosis. The findings, reported in the journal PLOS Digital Health, claims retinal images taken from the back of the eye are a way for doctors to estimate a person's biological age. The lack of access to bone density scans can lead to people with osteoporosis only finding out they have the condition after they've fractured a bone. For the study, the authors compared retinal imagery with bone mineral density scans and with fracture risk scores for some 2,000 older people from Singapore, as well as over 40,000 British participants. They found older biological age calculated using the retinal imagery was linked to lower bone mineral density and higher osteoporosis risk, meaning taking a retinal photograph could be another option for assessing the risk of fractures before they happen. Well, it's got to be one of the great moments in science. Researchers have discovered that insects feel pain. The findings, reported in the journal The Proceedings of the Royal Society B, show that the humble chirping cricket can feel pain. The authors found that the insects groom their antennae more in response to what could be considered painful levels of heat. Researchers applied a soldering iron heated to 65 degrees Celsius to one of the cricket's antennas and found they were significantly more likely to groom the stimulated antenna and did so for longer, key behaviours associated with pain. The realization that insects experience pain could have direct implications for the welfare of billions of farmed insects. A new study has shown that most Australian wild dogs have mostly dingo ancestry. The findings, reported in the journal Conservation Letters, are based on new genetic testing of a population of free-roaming canines in Australia, often labelled as wild dogs. Researchers from Adelaide University analysed more than 300 free-roaming canines across Australia and found that on average, just 11.7% of their DNA comes from domestic dog breeds. The rest is dingo. Well, it wouldn't be Friday without a good Bigfoot story for your listening and dancing pleasure.
These animals, in fact, are real.
I've seen them. They're here.
I'm having a really difficult time finding an explanation for this.
There's something on the hill.
I do think there's a squatch in these woods.
A former US Marine has now come forward with a remarkable tale of encountering a suspected Sasquatch during a training exercise at a restricted military base at Quantico in Virginia. Skeptics Tim Mendham says the incident, which occurred in the summer of 2005, was only revealed recently by the Bigfoot Field Researchers Association, the BFRO.
We all love a good Bigfoot story, and this isn't one of them. It's basically that some soldiers near Quantico in Virginia, military camp there, a former Marine has come forward with a, quote, remarkable account of encountering a suspected Sasquatch, or Bigfoot, whatever you like to call it, at a restricted military base. He said they were out in field training exercises at a mock urban environment. One evening, he and two other Marines were ordered to leave the location and travel through the woods to a pickup vehicle, approximately 500 to 700 metres away, which is not very far. But what they saw was there some trees being bent. This is what they said, or at least what this one fellow said. Trees being bent, and looking down, they saw a large, hairy creature with its back facing us. In other words, they didn't see a face. All they saw was pretty much a heavy thing pulling two trees together.
Oh, come on now. They were staggering out of a bar and they saw the bouncer.
Or it was a bear, or it was a lot of different things. But they hightailed it out of there. They said its proportions and movement did not resemble a human. They didn't see what it looked like. It had brown or reddish-brown hair. The one thing they did notice was that they experienced weird compass readings earlier in the evening. They don't say how much early in the evening, but what's that got to do with anything? I do not know, unless they're suggesting that Bigfoot is magnetic.
Thing nowadays is things like Sasquatch and that they're not just undiscovered species in the real world, they're supernatural, often from space.
That's why the term that we all know, UFO, has been changed because of sort of flying. People didn't like flying. It could be to unknown aerial phenomenon, still in the air. And then they changed it again to unknown anomalous phenomena. That drags in all the Bigfoot and weird creatures and psychic powers and all sorts of different things. So it's an all-encompassing and therefore meaningless title. But it's still unknown. And these people who were sort of 20 years ago that this thing supposedly happened, and it said it stayed with me forever. Yeah, you saw something pushing a tree over, apparently. You didn't see what it was. You saw a hairy back at night, I think it would be. I don't know. So, therefore, this is not one of the best Bigfoot stories. Then again, it's probably not one of the worst. In fact, they're all pretty terrible. So, this is just another one to throw in that is sort of Bigfoot on or close to a secret military camp.
That's the Skeptic's Tim Mendham, and this is SpaceTime. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGarry.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGarry.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.